Okay, well, welcome for coming to the this meeting. So this lecture number 16, computational modeling of molecules and materials. And it is second out of the four sets of presentations. The goal of the course is to computationally characterize properties of materials, and we are arranging the class by having several chapters building molecular models and optimizing geometry, characterizing alternating degrees of freedom from forgetting about equal degrees of freedom, and then there will be two more chapters on basic functional theory and excited states. So each chapter is accompanied by the lab sections, practical sessions, when one learns how to use the theories for modeling materials. But since the course is very short and time is limited to focus on one specific subject, these additional sessions are introduced so that each attendee of the class becomes expert in one subject and then teaches or refreshes knowledge of others how to do one or other specific thing. So today we will have the 8 presentations, and number 9 is postponed to the Tuesday. So there will be aspects of launching and analyzing output of the Gaussian software and extracting basic properties of the material that allow to characterize the properties, as well as some details as what to do in order to visualize concepts behind these observables and use these calculations for interpretation of experiment or designing the experiment. There is a last minute change in the order. Number 4 and 8 switched. And if you have never seen Windows operational system, it is here. If you have never seen PowerPoint, it is there. So you just select your name or number, click, and it will launch. We plan on having 5 minutes for presentation and a couple of minutes for questions. Questions are very much encouraged. And please please take into account that there will be some other scaling activities of other class attendees, so we need to try to be in time. First speaker is Steven Westra on the list of alternate structure methods.
I will try and speak quickly.
Okay.
I have a lot of information. So, like Dr. Killen said, I'll be speaking about electronic structure methods in Gaussian programming. So, first we cover some background of what is electronic structure methods. So, the basis of electronic structure methods is the Hartree-Fock method, which started in shortly around the time that Schrödinger originally developed the Schrödinger equation, and is a very basic approximation of the positions of electrons in a electronic field around an atom or molecule. So it makes a couple of assumptions, and that is that the Born-Oppenheimer approximation is inherent. All relativistic effects are ignored. The variational solution is assumed to be found via a series of discrete basic sum calculations rather than a continuous equation. And eigenfunctions are assumed to be described by a Slater determinant that they are capable of being described as a single number basis. And the mean field approximation is also applied. So other Gaussian methods, which are more developed and are capable of creating greater, more accurate approximations, are well, first in the Gaussian program, when you go to the method and calculate section, you'll see this arbitrary plot method. If you click on that, you'll of course be a list of different methods that you can use. Also, this basis set is also important, which I will be talking about later. So the methods that you'll most likely see will be the DTF, density functional theory, which is a more recent and more popular method involving the energy, the Hamiltonian of the Schrödinger equation being equal to the TVU, which is basically the approximates the energy and momentum and position of electrons around a basis atom set. And it's solved via a rather complex equation, which I did not have room to include here, so I'm asking about it later. The second one that you see is called the multiplicity theory, second order and fourth order, which is also a fifth order, but we do not have access to that in this program. And that's basically, it takes the Hamiltonian operator and adds a infinitesimal addition to account to sort of simulate the presence of other influencing electrons on the electron that's calculated. The second and fourth order, of course, refers to the order of the Schrödinger equation. And CCSD, coupled clusters, singles, and doubles. So that is a rather complex equation that calculates for clusters of electrons, singles and doubles referring to the excitation energy that it is. But specifically, it takes the Hamiltonian operator is equal to h times e to the t, with t being the excitation value for the single and double. It also has the option to calculate the triples that I'll talk about later. So, as I mentioned, basis sets, you'll see. So, the basis one is called STONG, Slater type orbital for n number of functions. That's the most basic one. The one that shows up by default is STO3G, which is 3 discrete functions for a Slater type orbital. It's a very basic, very crude approximation. It only is useful for more basic molecules such as hydrogen atoms and such. The next one you'll see is basically a format of x, y, z, g, where x is the number of calculations in the total equation. That would be equal to the ng top, the first one, and the y is equal to the calculations for the valence electrons. And so it's all typically the ones that are involved in reactions and are calculated separately. And usually a lesser number of calculations is used for the other electrons on an atom, and so it's not as important for any molecular interactions. And finally, the most complex and final one is CCPVNZ, so correlation consistent polarized valence zeta solutions. So the zeta solution refers to the solution you get from an STONG function. And that's basically, n would be like a doublet, either D, T, doublet, triplet, or quadruplet, Q, or some other number medium. And that would be, again, a very complicated equation for calculating only the valence electrons of an atom and assuming a polarized state. So just to show you how many equations we're talking about, for the CCPVNZ, this is the list of functions that you would be done for a molecule involving, for out of the molecule on an atom, for where that position is in the periodic table. For even a hydrogen, it's 5 functions just for that. So what I did to sort of test around with this is I logged into MobileX term on Dr. Killen's server. And I created a basic molecule. This is actually nickel tetracarbonyl. It's a complete closed set, no unpaired electrons, all in base levels. So that's basically molecule there. And I first did a calculation with the MP2321G basis set and method, and it gave a very nice, roughly similar one, showing that yes, the tetrahedral conformation is fairly consistent with what you would get for that molecule, and gave a very nice printout of values. As you can see, our occupied orbitals are all negative. We have basically a very stable molecule that is not going to fly apart on its own. So the next one I did was a CCSV using the 321G. And it, again, gave a very consistent with what is known structure for the molecule. But unfortunately, I don't have that last printout of orbital values for this because of what I did next. And that is, I ran a CCSV augmented CC PView QZ, because that has 84 functions, and there were 84 electrons in that molecule, so why not? That completely used up all of the server capability, and it did not actually complete. It timed me out and could not finish it. Keep in mind, the MP2 one was able to be finished in approximately 10 seconds. So I'm sorry, Dr. Killen, for using up all of your server resources. Yeah. Oh, and a comment. Those darn electrons being so common with waves and particles. Any questions?
Okay, well, thanks, Steven. Any questions to the presenter? And I would like to mention that we have several guests which we should acknowledge by applause. There is a co-director of CCAST facility, Dr. Khang Hoang, and PhD candidate Aaron Fordy, who is doing computational chemistry all the time. Yes. So, questions to Steven. On slide 13, you are showing orbitals, and if you can scroll up. Yes. So, like HOMO is number 42, if I can count. Does the number of the HOMO orbital depend on the choice of the basis set?
No.
Is there any situations when it can depend? And check, like, ask help of the class.
Right?
Yes, it changes with the basis.
Yeah. That's part of the reason why I chose the model that I did, is I know that it wouldn't have any funky, weird electron patterns. It's all paired electron sets.
Do you see a mechanism why number of HOMO may depend on the choice of basis set?
Yes, depending on whether you have, some of them mentioned it being polarized or unpolarized. If you have like a magnetic unpaired electron set, that would require a different basis set.
Okay, it is a paired electrons. And there is additional mechanism of using explicitly or skipping in approximate way the 4 electrons.
Yes.
So some basis set include 4 electrons, and then number of HOMO would increase. More questions to Steven? If no, let's thank him once again. Next presenter is Gwendorlene Chea, and she will overview types of calculations available in Gaussian, not in the selection of method, but in sense of which physical and chemical tasks can be addressed.
Alright. Hello, my name is Gwendorlene and as Dr. Killen said, I'm going to be giving a very brief list of tasks that are available in Gaussian. My presentation is unfortunately a lot less technical, but hopefully these are things that you've seen before, or other people actually go into more detail on how to perform some of these calculations. Alright, so I should actually mention that all My primary source for this presentation is from a Gaussian reference manual. And in that manual, it outlines different types of calculations. There are obviously more, but these are the 6 that are primarily Gaussian, one being geometry optimization, single point energy, frequency and thermochemistry, stability check, molecular orbitals and population analysis, and UV-VIS and electronic transition. We've all done geometry optimization, and it's pretty much a procedure that try to find the configuration of the minimal energy of the molecule. So here, as you're aware, when you construct your molecule, it's not in the perfect geometry. So the algorithm will calculate the wave function and the energy of your starting geometry, and this calculation is performed by calculating the force on each atom and evaluating the gradient of the energy with respect to the atomic position. It searches for the new geometry of the lower energy and repeats this process until you get the lowest possible energy it can find. There is a lot of information that you can obtain, and I'm not going to go through all the information you can obtain from each calculation at the presentation if you're interested in that. We also have single point energy. We stage a procedure that simply calculates the energy wave function as well as other requested properties based on your geometry. So the first thing you obviously want to do once you construct the structure is find the optimized geometry and then go to analyzing energy. There's usually done at the beginning of the study when you have a new molecule and you want to know the nature of the wave functions. Next, we have frequency and thermochemistry, and that calculates the vibration of the molecules that in question, and it also performs other parameters that you're interested in, including within this calculation. And you can see from this, you actually can get a lot of information, and there's multiple parts to it, but again, I'm not necessarily going to go into all the details. It's also important to perform stability check of your structure. And that determines whether the wave function computed by the molecular system is stable or not. I'm going to grab my water. I'm going to hold this up into one. Thank you for saying that to me. All right. So when if the wave state function is obviously unstable, it's going to affect your calculation. So, I mean, as I said, this is a very important step. And then we have molecular orbitals and population analysis, and it's a mathematical way of partitioning the wave from the function of electron density into a charge of a nucleus, bond order, as well as order related information. Also, the cubegen analysis is the most common population analysis performed, and for this calculation, you can get a lot of information, and all of that is listed below. And last but not least is the UV-VIS and electronic transition. So, and this has to do with the absorbance spectrum of your molecule. It can be characterized by vertical excitation energy. Most molecules have a bond, higher energy excited electronic state in addition to a ground state. These states may be sort of arising from a promotion of one electron from the occupied orbital into the ground state to a vacant higher energy orbital, the excitation of that electron from the occupied orbital to a higher electron occupied orbital when a photon of the same energy matches the difference between the two states interact with the module, and that's how you can get a UV-VIS spectrum. I don't know how to do this. I think it would be interesting, but I actually know how to do this, and I'm actually interested in calculating it to a common structure and seeing how that compares to a typical experimental. But I think you can obtain a lot of information from the UV-VIS, and I think that is about it. Like I said, all this information was taken from this reference, and it's a very good reference. That's why I have it here, because it actually goes into the different type of jobs that you can do. It doesn't give you detail on how to run any of the calculation, but it's really good at explaining each calculation, what it does, and why it's important in relation to quantum computational chemistry. But that's it, and I will be taking any questions.
Okay, thank you. So, any questions to the speaker?
Yes.
What is the latest version of Gaussian?
Isn't it like, I know it's not Gaussian 9 because I used that when I was like in undergrad as a while ago.
Yeah, because you mentioned that Gaussian 9 tutorial, which is a little bit old.
Yeah.
So the latest version would be like Gaussian 16.
Gaussian 16, alright. Okay, this was more readily available. And I thought it was a lot easier to understand.
Yeah.
The Gaussian is a relevant sequence, right?
Yeah.
But all users cannot use the Gaussian.
I mean, you just need to fill out a very simple form, decide a very simple form, return the form class, and you should be able to access the Gaussian.
Okay, so
It's free for everyone.
we don't need any permission from the department or.
No. You just need to sign the agreement, and then you should be able to access the Gaussian.
Thank you.
And if you want to use it, you should use it.
Sorry. More questions to the speaker? If no, let's thank Gwendorlene once again. So the next presentation is by Amirhadi Alesandi, and the presentation will be it is borrowed from the bottom of the schedule, and it shows he goes a little bit ahead of schedule, showing how to visualize results of calculations. But it is a good starter to have from the beginning a vision of what one can do in calculations.
Hello everybody. Today, in 5 minutes, I will try to have a brief review on what's isosurface, then isosurface of the density distribution, ESP potential, and Mulliken charge visualization. Just briefly want to see how it works, especially with the Gaussian. I don't want to go through the theory. So first, just start here. What is isosurface? Usually, isosurface is a 3D color map plot to show the points in the space, in the 3D dimension, that have the same value. For instance, maybe the value is pressure, temperature, or velocity. Here is the example that show isosurface of vorticity for a blade using the CFD simulation. So the usage of these are some examples of isosurface. This is, for example, chemical composition, a blade in the industrial application. Also, these are some isosurface that are plugged with MATLAB or maybe Python. Or there is also a lot of software that can generate the isosurfaces. So first, for instance, isosurface can be used for a molecular volume. Molecular volume can be determined by choosing an isosurface of electron density and then determining the volume inside of that surface. This could be utilized for several applications. For instance, determining whether a molecule will fit in an active site of an enzyme, predicting the liquid density, or determining the cavities. So, isosurface of electron density, usually predicting the exact location of the electrons in the space is not such that easy. Because of this, just a probability of the presence of the electron in the space is available. And electron densities are often rendered in terms of isosurface, with the size, which the size and the shape of this surface is a function of the density. Here is two isosurface for the electron density. For instance, here for 5 water molecules, and also here for silver and HC. I don't know what it is exactly, but the reference is available here. The next one. So how to do the isosurface using the Mahek Sadiq after doing energy calculation or optimization in the Gauss view. Sorry, in the Gauss view. From the results menu, surface and contours, and here you can generate the isosurface of the electron density. So the next brief topic is the visualization of molecular charge using Mulliken method. It depends on Mulliken population analysis. It's a very simple way to show the distribution of the charge, usually with some numbers, positive or negative, and also the color. Again, using the Gaussian, you can, after doing the calculation, energy, or optimization, go to the result, charge distribution, and here choose the Mulliken. you can set the range, the minimum and maximum, negative and positive, also the color, and there is some numbers and the colors. That negative number means that atoms have more electronegativity, and positive numbers also show some positive electropositivity. So, and the last topic for today is the electrostatic charge visualization. Usually, electrostatic charge, also called ESP charges, are computed from the electrostatic potential. Usually, ESP is evaluated at a series of points, usually at the van der Waals surface around the molecules, and then a curve fitting procedure is set to determine the partial charge on the nucleus, which results in generating the electrostatic potential. And similarly, for a benzene, go to the results, surface and contours, but here, this time, you can choose a new contour here and use ESP, electrostatic potential, to plot the ESP graph for your chemical composition or your molecule. And also here some example of isosurface for electron density for the materials that we used in the lab session yesterday. Also, this is a charge distribution for that composition. And finally, this is the ESP graph. Thank you for your attention.
Okay, let's thank any questions to the presenter? Yeah.
So, in addition to Gaussian, right?
Okay.
Yes, anything else? Any other software that you can use to visualize the ideal surface?
For sure, it should be, because there were several options, but I'm not such that familiar to give you some more details. Yeah.
Okay.
But just briefly, I show that I saw that.
Someone in the audience wants to
Salim, if you know.
What is the name?
JMO?
CHEM6? Okay, CHEM6. Okay. How about Westra?
I haven't used that one.
Okay, maybe Westra can read a lot of different fine. I mean, I mentioned that because what happens if something wrong with Gaussian, or you don't have money to buy Gaussian, you should think about using something else, right?
I will double check, because we are just learning this software, and I'm not such that familiar with that to go through the details, but I will try to learn it later.
All right.
Thanks, Nathan.
More questions to the speaker? Can you scroll one slide back? And explain the rightmost figure, what colors mean and how to interpret it.
So there is, here is for charge distribution. We have a minimum and maximum of the charge. Some positive value means electron positivity, and minus values means electron negativity. And also here, you can set the minimum and the maximum value. Usually these are the maximum and minimum available by the software. So depends on this range that you choose here. The Mulliken charge is plotted for the software.
Why the charge is fraction? Why the charge is not integer, like 0, 1, 2? What are the numbers there? Can you read and explain?
I think they are normalized, and the summation of them should be 0.
But how an atom can have the charge, like, let's go to your metal organic. You flip a couple of slides forward. Forward.
Oh, forward.
Yes. So how come that metal has 1.6 electrons less than needed? And where does this number come from?
So this number are from Mulliken population analysis.
Which comes from? How does it is connected to molecular orbital expansion coefficients? You were planning to add this equation to this slide.
He just left when you explained.
Huh?
He left yesterday.
Can you help him?
Yeah, this is the middle 1.6. That means the titanium is getting electron from the oxygen. So no, sorry, titanium is giving electron
yeah,
to
because
oxygen,
positive, right?
positive, and oxygen is negative because it's getting electron from titanium and the hydrogen. And the hydrogen is in between because it's it has a 50% electron.
It is correct, but it still doesn't give the answer, which is expansion coefficients of molecular orbitals over atomic orbitals squared. Right?
Yeah.
Good. Someone agrees. More questions to Amir? If not, then thank you once again.
Thank you.
And please do not be surprised if you go a little bit away from what is on the front page. Next speaker is Zhaofan Li. And he will continue attracting attention of everyone in the audience to nice figures and the way how to fabricate them. So he will tell more about molecular orbitals.
Excuse me, just please turn to the final page. Alright, so let's get started. Today I will just briefly introduce the spin and multiplicity and how to plot the molecular orbitals. So first, let's give a quick introduction to the spins. As we know, the particles or have sort of properties like the mass, charge, position, energy, and spin, angular momentum, or just spin for short, is one of those properties. And we also can sort these properties into two categories. So one is intrinsic, another is extrinsic. So the intrinsic means the properties the particles have because of what they are, including the mass and the charge. And this one is properties the particles have because of what they are doing, including the position and energy. So here the spin, just as it turns out here, falls into the first categories. And actually, the name should be the intrinsic angular momentum. The name would be more accurate than the spin. And it can spin up and spin down. So then, in the Gaussian view software, there are a lot of several options here. The charge, the different type of spin, and the multiplicity can be manually alterned here. And I just show one example of the checkpoint files. So we're able to specify the spin by changing some letters. For example, we can add in the U before the HF to make the spin unrestricted. And also, there are two values in front of the coordinates. So one value, the first one refers to the charge. For example, if the value is 0, which means the number of positive charge equals to the number of negative charge. Here, the value is 3, which means 3 more positive charge than the negative charge. And the second value refers to the multiplicity, which means how many configurations can have the same energy. So then, let's move on how to plot the molecular orbitals. It's the most cool part, and all of you are pretty familiar with it. So first, let's convert the checkpoint file into the text file by using the formchk command, just to have a suitable for visualization software. And then we also need to determine which orbital to plot. So here are several options. You can use more to go through entire files, and but it takes for a while, so it's better to choose the grep just to extract some relevant lines. So for example here, the occupied, which means the lower energy, the HOMO, and the visual means the high energy, the LUMO. So here we can determine which orbitals we want to plot. So then we'll generate the cubic file that containing the volumetric data in the form of cubic files by using this command. And here, the O means orbital, and these values here means which orbitals we want to plot. Then we're able to load all the cubic file into the Gaussian view software and choose the surfaces and the contours here in the result, the drop-down menu, and then we can just create a new surface for the molecules. And here, this value, the unit of this value is electrons per cubic astron. So here, just show some examples. It's a singlet, a multiplicity for the HOMO orbital and the LUMO orbital. And this one is for the double multiplicity, so with the help of dot killing. Here, let's show some examples we did last night. Okay, thank you, everybody. Any questions?
Okay. Thank Zhaofan, and the presentation is open for discussion.
And a student first,
If anyone, yeah.
Yeah.
So the ISO value, what is the reference? You said that the.
You mean this one?
Yes.
You
change it.
Yeah. It's ISO value. I think it's a parameter for the isosurface plot.
What will change if you modify this value?
We modify this value. Oh yeah, I think try this. It will change the not the shape of the.
Just show by hand. What changes if you make it smaller? How orbital will change if you make this ISO value smaller?
So, for example, if we increase this value, the shape will shrink. Yeah, it's like it's like a range of the values. Yeah, or if the value is short, we can see more the values. The more values will show in the figures.
Number of electrons.
Which
Number
one?
of electrons.
Or electrons.
The more value means less number of
It's
Density, probability in this area. Yeah.
with higher value, ISO value, you focus on the high density area.
Yes, very good formulation. Many thanks for.
Okay, my question.
Please.
I have two questions. Can you get back to the input file with 3 and 2, something to do with multiplicity and also? So here, 3 for jobs, 2 for multiplicity.
yes.
How do you choose it?
Okay, I think it depends on the molecules. Yeah. For example, the first value means the charge.
So in this case, what does it mean? Does it mean that titanium 3+?
Yes, it's for example the 3+. We choose the 3, which means there are 3 more positive charges than the negative charges. And also the second value means the multiplicity.
What does it mean?
It means for example, if the value is 2, which means there are 2 configurations which have the same energy. For example, 1 spin up and 1 spin down, which means there are only 1 free electrons out of the molecules.
It is in the right direction.
So what happened is that at 3, I get it to 4 or 5. What's going to happen with that way?
Or actually, I didn't try it.
Okay,
Or I think probably it will destroy, or all the electrons will go out. So there will be some error for the Gaussian view software.
The high multiplicity is needed for magnetic materials. If you do several magnetic atoms, you may need high multiplicity. So,
I think that was the question about this day when you said that we can have 3 the first distributions where they both spin up, both spin down, and then one
Yeah,
spin
no,
up.
one up and one down.
Doublet,
Triplet.
triplet, sorry,
Yes.
triplet.
So with the both spin up and both spin down, would that not be against the project?
I see.
No. If you put two spin down on the same orbital,
Yes.
it will be against our exclusion principle, and Gaussian will not allow you to do so. But if you put one spin down on one orbital and another spin down on another orbital, then it will be legitimate triplet configuration. Okay? Thank you. Really good question.
The second, that's a good question. The second question has something to do with the HOMO and the.
Yes.
Okay. So when you do the visualization, you should just focus on the HOMO and the LOMO. So the highest occupied state and the lowest unoccupied.
Right.
Why? Why they are important?
We can determine the band gap through these two values. So for example, if there is some overlap between which means there's no band gap, the material it tends to be the kinetic.
Okay. In addition to the band gap, what else we can learn from this? By looking at the charge distribution on the HOMO and the LOMO.
Charge distribution.
You have some very nice figures, associated with the HOMO and the LUMO. Can you show it? Can you go? That's that. Okay. So you had a HOMO and a LUMO.
Right.
What else can we learn from this? It looks nice, but in addition to being nice, what else we can learn from this?
Okay, the electron density probability of this figure and also we can check, for example, some atoms will attract electrons, or some atoms will repulsion or elect some electrons.
Yeah,
from this figure.
Great. And how to project your last sentence onto this figure? Like which atoms attract electrons and which atom repel electrons for HOMO and LUMO and how?
So, for example, it's the oxygen. It will attract more electrons than the hydrogen and the hydrogen. Or for example, the hydrogen will lose some electrons. The more electrons just around the oxygen.
Yeah, you're going in the right direction. Yeah. But the question is just to emphasize the importance of the electronic structure near the band gap region. So lots of properties are determined by the figure, by either transport property, electronic properties, or even optical.
More questions to this interesting talk. I have a couple. So if you scroll back, more, here. You are telling cubegen O MO35.
Yes.
So between little o and MO, one sometimes can put the letters A and B.
Oh yes.
So please explain when you have to place them, when you can skip them, like what is the rule of thumb, how to interpret what are the letters.
Okay. So if we just put the A before the MO, which means it will show the alpha, or we can see just show the spin up. If we change to the beta, it will show the spin down.
Okay, and can you illustrate it with your last slide?
So for example, here it's a. Oh, but yeah, we need to change the units. Okay, it's a just show the spin up and show the spin down for the different orbital energies.
And orbitals look differently for spin up and spin down.
Yeah, it's a spin up and a spin down, and here it's the band gap.
Okay, more questions? If no, I thank Zhaofan once again. And now there is an trick who will be next, because let's go according to the original schedule, and next speaker will be Yangchao Liao, and then we will continue everything as scheduled.
So good morning, everybody. So today I'm going to talk about how to analyze Gaussian output file without Gaussian view. The contents of this topic are including how to extract total energy, ionization energy, the electron affinity, and the energy gap of the output file. So first we need to create the model and calculate the model in Gaussian. As you can see from the top figure, this is the model I used in today's presentation. And if we can see from the bottom figure, the Gaussian calculation summary of the model, actually we can get the total energy of this model. How can we get the total energy, HOMO energy, and NUMO energy without Gaussian view? So firstly, Gaussian writes its output file as input file lem.log. That means I limit my input file limit as model 1. So that means the output file also be model 1.log. Okay, so we can also use ls command to list directory contents. As you can see, we have the output file, log, output file, and the input file, right? So output file contains a lot of information. But today we only I only focus on the total energy and ionization. Ionization energy we also create as HOMO energy, and the electron affinity we also create as NUMO energy. So first we can use more command to read the output file. For example, when I running a more input file name.log and we press enter, we can get the a lot of information. This information will display on our screen. As you can see, the total energy of this model is shown here, E, RHF, and this is the total energy of optimized geometry with the unit of atomic unit. I should mention you that 1 atomic unit equals to 27.12 electron watt. And we can also get the HOMO energy of this model. As you can see, the whole HOMO energy is the last value of the occupied eigenvalues, right? The last value of the occupied eigenvalues. And the NUMO energy is the first value of the virtual eigenvalues. Okay, the first value of virtual eigenvalues. So we can also use grep command to find and inspect the information what we wanted. For example, we can use grep SCF input file lem.log to find out the total energy of this model. Actually, it should be same. I just put the wrong screenshot for this presentation. Right? It's the same as the previous one. Okay, and we can also use grep -n alpha input file lem.log to find out the HOMO energy and the NUMO energy for this model. So in conclusion, we have get the total energy of this model, and we can also get the ionization energy for this model. As you can see, the not just a value of the blue line is the ionization energy we call it as HOMO energy, and the electron affinity. That means the smallest value of the red line. So what is the energy gap? The energy gap can be obtained by using HOMO energy and the NUMO energy. That means the energy gap is equal to NUMO energy minus HOMO energy. So this is all for my today's presentation.
Okay. Other questions to the talk of Yangchao?
Should we make it a requirement that every student has to ask?
No requirements. It's encouraged but not mandated.
All right.
Please
go ahead. Please go ahead. Okay. Why the energy at the HOMO is the ionization energy? Why the ionization energy equal to the energy at the HOMO?
Why the energy gap equals to normal energy minus Homer energy?
No. The blue one. The blue one.
Blue one, yeah.
Yeah. No, well, number 2. Why the ionization energy equal to the energy at the HOMO?
Why it is called ionization energy?
Well, why we call it is Homer energy. Homer energy means we can grow a little bit back. Homer energy means the orbital energy of the highest occupied molecular orbital.
And yet, what is the ionization energy?
Ionization energy.
Ionization energy. That's number 2. What is ionization energy?
Definition.
Definition.
If you're not sure, ask for the class. Let's do like collective brain.
Have me too.
If you want to take an electron from the metal outside the air, just the ionization energy.
Right.
Yeah.
That is the energy that is needed in order to remove one electron from the system and put it, infinitely far away. Right?
Yes. Yeah. Okay.
And when you remove one electron from the system, you remove it from the highest occupied state as the whole. Right?
Yeah.
And that's why in this case, and hopefully the total energy is with a reference to the radius, right? In Gaussian. Okay,
Yes.
so it means that in this case, the energy at the HOMO equal to the ionization energy. Yeah, because when you have to remove the electron, one electron from there and put it into the radius.
Yes. Thank you.
More questions to Yangchao? If not, thank you once again.
Thank you, everybody.
And the next presentation is by Mahek Sadiq. So she will help us, she will teach us how to use symmetry in Gaussian calculations.
Good afternoon, I am Mahek Sadiq, and I will be presenting on symmetry groups in Gaussian software. First of all, before starting, I would like to explain what is symmetry. Well, symmetry is if we divide something by planes, we will have equal halves. That mirror reflection, it will be kind of mirror reflection. And what's the benefit of using symmetry? So if some molecules or particles have the same kind of symmetry, it helps us in classification, determining their properties. We don't have to go deeper. We can identify what kind of properties they might have, and we can bring out general conclusions. So I did my symmetry, I did this upon naphthalene, that is combination of two benzene molecules, two benzene rings, and naphthalene has bilateral symmetry. So now coming to the steps to symmetrize in Gaussian. So first of all, we build the molecule using the builder, the viewer, and then we go to calculate for doing proceeding to symmetrize. So we go to calculate, and then after going to calculate, we go to Gaussian calculation setup. Then under job type, we first optimize, and after optimizing it, we again go to under job type we go to optimize, and then in method we optimize it, and after optimizing and saving the file on the same file, we again go to job type and select energy. After selecting energy, we go to method. The method here, I've applied is Hardy form. It's applied to waveforms and it's applied to determine waveforms and the energy. So I've applied Hardy form. The basis set is 321G and the spin is singlet. So now, what is single point? Though it has been explained in the previous presentations, let me recall it. Single point determines the potential energy of a molecule with that specific atomic arrangements. So, with that specific atomic arrangement, the potential energy is the single point. And now, coming to 321G. So, if I want to explain it, I'll start from scratch. So, let's think about double zeta basis set. The double zeta basis set is applied to determine the energy of each orbital in an atom for a molecule. So, but this is time consuming. So what the scientists did is they applied double zeta basis set to the outer orbital, and to the inner orbital they applied single Slater orbital, or the STO theory, the Slater type orbital theory. So the combination of double zeta basis set to the outer orbital and single Slater orbital theory to the inner orbital is known as split valence basis set, and this is what we are applying. So the most common type of split valence basis set is 321G, where 3 is the number of Gaussian functions, the total number of Gaussian functions applied to the inner orbitals. 2 indicates the number of Gaussian functions for the first Slater type orbital, and 1 indicates the number of Gaussian functions to the second Slater type orbital. So that's why we apply 321G basis set. After applying this under method, we go to general and we check whether the ignore symmetry is deselected or not. That is, symmetry is selected. Afterwards, we run this and we check the result, and we can see that this is the energy that we get. And this is the job CPU time, which is 49.5 seconds. Now, we go back to general again and we select the ignore symmetry. That is, we are not selecting symmetry now. And the result that we get is the same energy, but the job time has increased to 50.4 seconds. So why do we use symmetry in Gaussian? It reduces the CPU, the disk storage, and the input-output requirements, and it reduces the job time, as we've seen. It reduces the calculation steps, and finally, it maintains accuracy. For the molecule, we can only apply for the molecules that have symmetry.
Okay, but is it what? So questions?
So, anyone else first? So when not to use, okay, when not to check on no symmetry?
When there, for example, in benzene it has symmetry in naphthalene, but for we work with TiOH4, we don't need symmetry there. And for example, yes, for certain molecules we have symmetry, and we don't need symmetry in the, we don't select it where we don't need it, for example, example that I gave.
So what are the points, imposing symmetry? When we impose symmetry on a molecule, we put some constraint on whatever it is.
Yeah.
Right? And I would think that we do so because we know for sure that this molecule is going to have this structure. Right? But in certain situations that we are not really sure about the structure of the molecule. So in that case, should we check on no symmetry, or should we check on no symmetry, or we should not check on no symmetry?
I think we should try with both and check the CPU job.
Good answer. You can do both and see if there's something. Yeah.
More questions to Mahek? If not, thank her once again. And the next presentation is by Raju. I'm trying to learn to pronounce his name. Mozammal Kamal Raju. And he will. It's quite important talk because he will continue description how to analyze output of the Gaussian and overview several subjects that were presented before.
Hello everyone, thank you, Dr. Dimitri, for giving the floor. So the topic of my presentation is nomenclature of bases. Power script is struct density DOS from .log file and definition of DOS. So first of all, the basis set, if we want to go through the basis set, it's a huge topic. It's maybe we need another semester to study the basis set. So in general, how is basis set? Basis set is a set of functions. Set of functions or vectors that span in space, and in quantum chemistry, what we using the basis set to describe the shape of the orbital. To describe the shape of the orbital, especially in our lab, quantum computation chemistry, we using Hardy-Fock theory. So on that, the basis set is used for one electronic orbit, one electronic function for the many there is a superposition of many electron orbits. So if you see the equation, this is the phi I is the molecular orbit equals to C mu I is the expansion coefficient, and F is the LCAO, that means linear combination of atomic orbitals. So if you see, if we want to do the basis set on Gaussian view, Gauss view or Gaussian, so if I go through the basis set, if we select this basis set drop down menu, we see a lot of basis sets. So therefore, the different type of molecules, we use different type of basis sets. So I will discuss later a little bit, just superficially maybe. So what are the functions we used in this basis sets? What are the functions? There are a lot of functions. The most common function we are using STO type orbitals. These are the most common type function. And GTO, Gaussian type. These are the equations. Previously, Stephen and Mahek, they say something about this function STO, and also they mention about the zeta. Here is the zeta. So, zeta function, and there is another one updated on CGTO, the concentrated Gaussian. So you see, 3 Gaussian function has been concentrated into one. And polarization function, you see this d orbital has been added to the p orbital to get the ultimate orbital. And diffuse function, in diffuse function they use very small exponentials, because in diffusion we don't want, there is not that much variation, a little bit. So the nomenclature of basis set. The first, there are a lot of, I said already, there are a lot of basis sets. I will discuss a couple of them. So first of all, the minimal basis sets. This is the most common type of basis sets they are used. So already discussed by Mahek, he said. So STO3G. So STO means Slater type orbit. So 3G, there has three primitive functions, 3 Gaussian function, primitive Gaussian function has been used. Here 4, here 6 has been used. And if you see here the steric, this is used because they use the polarization function also. So another function is spheric balanced basis set, also named after John Popo, the inventor. So here, if you see the 321 like this, the structure, here is the explanation. The first 3 is x is the number of the function used for the core orbitals, and x or y, z, w, v, this is the number of the function, Gaussian function has been used for the valence orbitals. And you see here the plus, if there is one plus, that means the diffuse function only used for the heavy orbitals, and if there is double plus, that means the diffuse function has been used for all the orbitals, including hydrogen, because hydrogen is the lightest atom. And if there is steric, that means it has been used for the heavy orbital. If double steric, that means it has been used for all the atoms, all the molecules. The other one is a consistent, correlation consistent basis set, or it can be said as CC basis set. So there are this has been invented by Dunning and his co-worker. This is used for the post analysis of Hartree-Fock method. And actually this is the empirical technique that you got from your experiment. So there are a lot of types. The PBDZ, that means DZ means double beta. CCP means correlation consistent polarized. These P all are for, because the function they are using polarized function, and they used, like I said before, the Slater type orbital. They used double zeta, triple zeta, and quadruple zeta, and so on. There is another on the Karlsruhe basis sets. They are named after Karlsruhe. This is also a polarized function. Polarization function has been used. So if you see, this is split balance. Split balance, when you use a parenthesis like this, that means the polarization function has not applied to the light atom hydrogen. But when there is no parenthesis, that means all the atoms, polarization function has been applied to all the atoms, including hydrogen. So you see, it also has the double zeta, triple zeta functions have been used for this function. Also, they use the diffuse function. So this is more advanced basis sets to be used for heavy atoms or bigger atoms, molecules. So there are also some other basis sets. So I don't want to discuss them later. But what are the application where we can apply these basis sets? So you see this chart. The Slater determinant. I say this is the most common. It has been used for the very light, small molecules. But if you go for the more heavier, bigger molecules like lanthanum, lithium, so you see this other type of basis sets has been used, and also the CC has been used for the bigger molecules to get the more accurate and better results. So that's for the basis sets. And now I'll do the next topic, the form snip density of states from dot log file. So this is the equation the Gaussian software used from the Fock equation is the Fock matrix, and from this determinant we can find the eigenenergy EI. So this energy is EI, different energies for different orbitals. Okay, so this is the code we used in our program, in our terminal in MobaXprom. So the PAL is the command to extract the energy from this file, the log file, and make it into DOS file. I'll show it later, Como and Lumo. And this is the input file, which file from you want to extract the energy. And these are the parameters we want to use to generate our DOS curve. So first, the PAL command to extract the energy. You see the orbital energies for different orbitals. The energies have been extracted. So these are the HOMO, the two highest occupied orbital, molecular orbital, and these are the LUMO, lowest unoccupied molecular orbital. And we can see by executing the command mode e/the file name, e_the file name, and that creates a file. This command creates a file named e_the file input file what I gave, and these are the parameters it uses. So it used 100 steps for calculation. The bandwidth, here we use the Gaussian as an example. If we change the bandwidth, it will be more narrow. If we use more higher bandwidth, it will be wider. But it's better to use narrow because the accuracy and the location of the energy orbits, it will give you the more accurate outcome about the location of the energy. Sorry, state of the energy orbital. And the 5 electron volt means that it will take the energy from the LUMO to 5 electron volt up, and the 5 electron down from the LUMO. So here you see for HOMO I got minus 13.86. So for this 5 I get almost 18. So for the HOMO I got 18 here, okay, 18, and it's almost 0. So I got 5, almost close to 5. So that's how this plot has been drawn. And now comes the definition of DOS. What is DOS? DOS is the number of interval of number of states in a certain period of interval of energy. How many states we have in between two energy levels? That defines the DOS. So high DOS specifies the many states available for occupation, and 0 DOS means there is no state available for occupation. So there is a pictorial view of the HOMO and LUMO. This is the valence band. So these are occupied, okay, and these are the unoccupied conduction band. So these are the density function. So this is how the electron can be energy can be distributed. And we already discussed some many other person representative has been said that the energy between conduction and valence band or HOMO or LUMO is the energy band gap. That's how that's where the DOS gives us the idea the material we are dealing with, whether it is metal, semiconductor, or insulator.
Okay, thank you, Raju. Many thanks to those who are so inclined to invest time into this course, and any questions to Raju are appreciated. The molecule that you were doing in class, is it metal, semiconductor, or insulator?
Let me see. I didn't. So it's insulator.
Okay, very good. Let's thank Raju once again. And last but not least, Salim, Thomas. So I think we are going as far as we progress from the beginning to the end. We get stronger and heavier theory proportion increased in the talks. So the presentation by Salim will include heavy equations. So who likes equations will enjoy this talk.
So hello everyone. Today my presentation is going to be on how to draw numerical data using NumPlot software. Using NumPlot software, and as an example, I'm going to show how to plot different steps which I explained definition of. And I'm also going to explain our molecular orbitals in a very introductory way, and the formchk and cubegen command lines, and the concept of isosurfaces. So NuPlot is a very useful plotting software that has a lot of good features, including generation of two-dimensional and three-dimensional plots for functional and numerical data, and the ability to support many different types of file formats and to be able to output many different types of file formats. And also you can have
Your call will be disconnected.
You can also have the choice of interactive using the window or script command lines inputs. And how to use it in class? So far, what we use is this NuPlot and then this command line to plot using NuPlot. But actually, when you open the program itself, these are the lines that are already being done for us to plot the density of states. So in here we have the first line that's setting the terminal postscript using the font of choice with the size of choice, and then the output as an image with ps.ps file, and setting the x label, y labels, and then plotting the density of state of all alpha spins. That's going to be that's the input, right? And then and this means actually you means using first column as x-axis, second column as y-axis, and then the title up with line. So this is why we have this this plot. And the log file was generated using the Perl script that you explained earlier. So this plot was the density of state with respect to the molecular, the orbital energies, and so it's going to be important maybe to have a little bit of information about molecular orbitals. So molecular. I'm going to start by saying that it's an important concept. Molecular orbitals. It describes the properties, the wave-like properties of electrons. And so Hartree Fock is the person who tried to approximate the solution of the time-independent Schrödinger equations, assuming that the motion of an electron doesn't depend on. The electron doesn't depend on the other electrons that are the motions of the other electrons close to it. So that's the main assumption that he did, and that's what I wrote here. It can by a single particle function that doesn't depend explicitly on the motion of the other electrons. So in this case, I'm going to give a simple example of the hydrogen atom, where we have another electron. So he's assuming that this electron that's going to form that hydrogen minus, that ion, is not going to depend on the electron that's already there. So they cannot occupy the same orbital. It has to be in a different orbital, like the Pauli principle, Pauli exclusion principle says. So this assumption tells us, okay, from the main Hamiltonian, after the Born-Oppenheimer approximation, we can separate the electronic part and then the nuclei part. And so it's important to really solve this, to solve or to have an approximation for this Schrödinger equation, because it takes a lot of computations, and it's very, very heavy, and it's, besides, the hydrogen atom is going to be very, very, very hard to solve. So after the Born-Oppenheimer approximation, so Hartree-Fock theory tells us that because we don't have any because the interactions between the electron and then the incoming electrons are negligible. The wave function.
No, it cannot be negligible.
Right?
If there's no interaction between the electron and nuclei, your atom has fallen apart. Right?
Yes, as is apart, but because of the bond.
So the main point is the nucleus is much heavier than electron. So electrons moving very fast. So as the first approximation, you can assume that when the electron is moving around, you can fix the position of the nuclei, right? So that the basic idea behind that Born-Oppenheimer approximation. Certainly, there is interaction between electron and the nuclei, right?
Yes, there is, yes.
It's just that to make it easier for the calculation, you fix the position of the nuclei, and then you do the calculation for for the electrons. And then the next step would be to move the nuclei and do the calculation again. That's true, right?
Okay.
So it had to have interaction with the electron.
Yes.
Okay. Yeah.
So I was going to say yes. So because of this assumption, then the wave function can be described as a product of other wave functions for other electrons.
Mm-hmm.
So, and the problem with that was that it didn't satisfy the anti-symmetry principle, which introduces the spin concept here as this projection of the angular momentum on the y-axis. So and here so we have to satisfy this anti-symmetry principle. So the eigenfunction as a sum of other eigenfunctions in the spatial orbital is going to turn into the spin orbitals, right? And spin orbital is it's just the spatial orbital times the alpha or beta function, which describes the spin up and down. So this anti-symmetry principle, in the case of two electrons, tells us that when we switch the spin and
just swap electrons.
Yes. When we spin them, it's going to be negative, right? The wave function is going to turn into negative. But then the Hardy-Fock approximation didn't satisfy that, and the only way that it could satisfy it for the case of two electrons is that if the wave function looked like this, and this this equation actually can be represented by a determinant which was called the Slater determinant. And in the case of many electrons, this is how the Slater determinant will look like. And this also confirms the Hardy-Fock theory that the electron is moving independently of other electrons, except that the repulsion from the average of all the other electrons surround close to it. So in here, after the Slater determinant, the electronic total energy can be represented by this bracket notation with the Hamiltonian as a operator, and also chemists represented this as this integral, and because of this symmetry here, because we have this wave function here and wave function, it's possible to, and usually the energies are because it looks like this, the energy is supposed to be higher than the actual energy that we have here because of this theory. I forgot the name of it, but the energy is supposed to be higher So we can change the parameters of this wave function to minimize the energy, and that's going to give us the molecular orbitals. So the solutions of this thing, and this is what the computer does for us using the Hardy-Fock method. that was the hard part. So after that, so like you said, from the after we do the Hardy-Fock calculations using Gauss view, and we use the Perl script to store them in this like after, no, actually even after like using Gauss view, after we do the Hardy-Fock calculations, we generate this checkpoint file which stores all the information right during the Hardy-Fock operations. And so this checkpoint file is going to be formatted into another type of file that we call the formatted checkpoint file, which can be used as an input to be able to visualize the molecular orbitals. So this is how it's written, right? Formchk, and then the options which just you can just like using different versions of Gaussian, for example, there is different options that you can use. But then all you have to do is the checkpoint file, and then you don't even have to write the name of the formatted file, because if not, I mean, if you don't do that, it's still going to create the formatted file, the f checkpoint file, as the same name as the checkpoint file, with just f check, formatted check. And then after that, after you get that formatted check, you can use cubegen to use this formatted checkpoint file as an input to be able to generate this output as a cube.cube file, which can be used to be visualized using Gauss view as well. So in the case of the density of states,
not density of states, just density. It's not density of states. It's charge density.
Yes, in here, yes, in this example. But in the case of the density of the one we did in class, no, sorry. Instead of the, for the molecular orbitals, like Raju explained, we have to type molecular orbitals and then equals to the number of the molecular orbital that you want to visualize, right? Even if it's the LUMO or the HOMO or LUMO. But in the case of the charge density, you can type density as well. So this cubegen is very useful, and this is how you use it, right? Cubegen, number of processors or memory available to be able to do the calculations needed to be able to visualize them. And kind here, in kind, this is where you choose molecular orbitals or alpha molecular orbitals, beta, or density or spin density or alpha or beta spin densities, or potential for electrostatic potential, and generate this output file as a cube that you can visualize using Gauss view. And the number of points per default is 80 points per side of the cube, so 80 to the power 3, and you can change it, make it more accurate, but takes more processors or more memory as well. So this is how the output is going to look like for molecular orbitals, or for density, or for spin density, or for potential total electrostatic potential energy, right? Electrostatic potential energy that the previous presentations explained. So all you have to do is click on result and then surface contours, and then after that we get this result, right? With this, that's called isosurface, which is basically the representation in 3 dimensions of. If I have to give an example, if you look at like a mountain, for example, that has to be represented on a topological like map or something like that in 2 dimensionals, you're going to see contours, right, which describe the same height, right, with different. And then in 3 dimensions, the 3 dimensions version of that is what's this isosurface. So it describes the surfaces with the same energy, same value, right?
Of function, which is
of any
density
function.
of a function.
It can be any function, right? So for the height, for example, is going to be the same height, and then So it depends on the function. But it's just a three-dimensional representation of that contour line. And here the ISO value, of course, is how focused it is on higher or lower values. So it can be higher, it can be lower, depending on how you change it. So in conclusion, GNU plot is very useful for plotting two-dimensional molecular orbitals are important to understand. It's a basis for almost everything here. Formchk to format checkpoint into formatted checkpoint that can be used as an input for cubegen to generate output as cubes, and then that can be visualized these isosurfaces that you can also make bigger or smaller, or focusing on higher values or lower values. So thank you very much for listening.
Okay, thanks, Salim. Do you want questions?
It's the last presentation. So
I
have the last one.
Yes, I have a killer question.
Okay.
What is exchange?
Huh?
What is exchange? Do you have what is the difference between Coulomb and exchange, and do you have any equation that shows it?
Coulomb
and exchange.
and exchange.
Mm-hmm. Let's find the answer together. Right? Yeah, here. Like your last equation on this side.
Mm-hmm.
So what should be the values of this I, J, K, L for?
This is for two electrons. This is the
right. But they can repel each other or give negative energy, which will correspond to quasi-attraction.
Yes. Well, they're supposed to be repelling each other.
So you see that your brackets have the indices I, J, K, L.
Yes.
So if the first two indices equal to each other and last two indices equal to each other, it will be repulsion?
No, if they're equal to each other, then isn't it the same as having two electrons in the same orbital?
Yes.
That would be zero,
it will be repulsion. It will be density.
Sorry, I don't understand. If I equals J or N equals K equals L?
No. If first two indices are equal to each other and last two indices equal to each other.
So we're going to have I here, and then
K
there.
Then it will be density of electrons in point 1, repelling from density of electrons at point 2.
Yes.
But if the indices are deviating from this rule, if they're swapping, it will be something different than Coulomb attraction, and it will give the negative contribution to the total energy, and it is called exchange.
So there's possibility.
Just say yes.
Say yes.
Yes. Good. More questions to Salim? If no, thank you once again. So many thanks to all presenters, everyone who it took a lot of efforts in addition to regular homeworks, lab works, and different assignments. So it is worth of additional credit equivalent to successful homework. So you're doing great towards completing the course. I hope the recordings were going well and you get the link to this recording. So if you need to watch it again, like yourself or your partner, and have a nice weekend. See you next week. Meeting is complete.
Thank you.